Thank you. So I'm very happy to be presenting joint work with Nikhil Agarwal. The title is Identification and Estimation in Manipulable Assignment Mechanisms. So when we think about doing analysis in a market, we typically need estimates of preferences. This is because once we have preferences, we can construct counterfactuals, we can simulate them, and analyze the effects of different policies in terms of efficiency or distributional consequences. And we hope that we can do the same thing when we analyze assignment mechanisms, such as those that are typically used to assign students to schools in many public school districts. So sometimes there is a direct link between behavior and preferences. For example, when we see that the consumer buys a product, we can infer that that product provided that consumer with the highest indirect utility among all the products that are available. And in the same way, if we have a mechanism that is solvable in dominant strategies, then we can interpret behavior that is reports of agents to the mechanism in a direct way. However, there are some cases where the link between preferences and actions is more subtle, and these are cases where the strategic incentives are complex. For example, in auctions, we would never, in first price auctions, we would never think that the bid that the bidder submits to the auction is the actual valuation, because bidders have incentives to bid below their value in order to earn some rents. In the same way, we have a mechanism such as the Boston mechanism that provide parents some incentives to report to the mechanism a rank order list that is different than the actual ordinal preferences that parents have. So the research question is, can we actually learn preferences from data on ordinal reports submitted to a manipulable assignment mechanism? So to give an idea, here we have all the school districts that use some manipulable mechanisms, and we have some school districts that use a non-manipulable mechanism. And over time, we're getting more school districts that use non-manipulable mechanisms, but for a long while, most of them were using manipulable mechanisms, okay? So what we're going to be looking at is a single unit assignment mechanism without monetary transfers, and the mechanism is going to use ordinal preferences to allocate objects across individuals. And for example, this example includes serial dictatorships, the fair acceptance, and Boston mechanism. We're going to assume that the researcher has data from a market with many participants and a few choices, that is, many students and a few schools. And the researcher knows the mechanism that is being used, and maybe the capacities of the schools, and maybe some student and school characteristics. So what we're going to do is to show you some evidence from Cambridge, where we're going to try to convince you that there are significant incentives to be very careful with the school that you rank first. So the school that you tell the public district which is the school that you think is the best that you want to be assigned. And we're going to show you that students are responding to some strategic incentives. And for that, we're going to use some discontinuity analysis. And then we're going to have an estimation strategy that consists on two parts. The first is that we're going to try to estimate the assignment probabilities that is linked to each report. So the key idea of this paper is that we're going to be thinking of each report that you submit to the mechanism as returning a lottery over assignment. That is, when you submit, first I like school A, then B, and then C, then that means that then the mechanism is going to return to you a vector of probabilities that you get assigned to each school. So the first step is going to be to estimate those probabilities, and in the second step, we're going to estimate preferences parameters, assuming that the report to the mechanism is optimal, given what other people are doing. So, and then we're going to apply this again to Cambridge, and we're going to compare preference estimates that we get if we assume that people are behaving truthfully, or if we assume that people are behaving in a sophisticated way, that is, if they understand the mechanism. We're going to ask what fraction of students are assigned to their actual top choice. And we're going to compare that number with the number that I have above, that is that 82% of kids get assigned to the school that they rank first. But in fact, we're going to argue that the number of students that get assigned to a school that they really prefer is much lower. It's a little bit low. So, and then we're going to compute a counterfactual, that is, what would happen if instead of having the Boston mechanism or a variant of the Boston mechanism that we have right now, we change the mechanism to a strategy-proof mechanism such as deferred acceptance. Okay? So this is related to different strands of literature that in order of time I'm going to skip. So first, let me describe the data. First, let me tell you about the Cambridge public system, and then I'm going to deal a little bit more with the theory. So, so there are 13 schools in Cambridge. Typically, there are 470 seats available for 426 students. And a third of them qualify for the free lunch program, so that they qualify for a federal subsidy. And half of them are white, and most of them speak English at home. The closest school to your typical student is half a mile away, and the average school from of the 13 is about 2 miles away. You can think of Cambridge being 5 miles from east to west. So the mechanism by which students are assigned to schools is as follows. You as a student receive priority for 2 reasons. First, because you have a sibling that is attending to that school. And second, because that school is one of the 2 closest schools to your house. Okay? So the way that the mechanisms work is as follows. First, your application is sent to the school that you ranked first. And then that school is going to order all the students according to their sibling priority first, then proximity priority, and then breaking ties with a lottery. So what they're going to do is assign all the students according to the priority list up to a point where the capacity is reached, and then they're going to reject the rest of the students. Okay? If you're one of the rejected students, your file is going to be sent to the school that you ranked second, and that school is going to reserve all the files from all the students that ranked second and were rejected, and it's going to do the same thing and assign the students as long as that school has any seat left after the first round when they allocated all the students. Okay, the only caveat, the only reason why this is not a traditional Boston mechanism is that for the purpose of the mechanism, each school has 2 programs, one that is for paid lunch kids and one that is for free lunch kids. This is because they want to keep a balance of socioeconomic status within schools. So let me tell you what happens in the data. 82% of the kids get assigned to their top choice, and 10% of the kids remain unassigned. These 2 numbers are very different. If we look at paid lunch kids, that is 76%, and free lunch kids that are 92%. This is because roughly the programs have the same capacities for paid lunch and no paid lunch kids, but I told you that there were more paid lunch kids. So essentially, here you can see that for them, the market is more competitive. For paid lunch kids, the market is more competitive. The other important thing is that most people rank 3 schools. 87% of people rank actually 3 schools. So here I want to convince you that if you're a parent that you're participating in this mechanism, you need to think very hard what you're going to rank first. What is the school that you're going to rank first? So what we have done here is to order all schools according to the number of times that school appears ranked first in a typical year. And this is the order. Graham Parks is a school that is ranked first the most often with 60 times the median number. And here what we have is the first student that was rejected. So this is after the school filled the capacity. What was the priority of the first guy that was rejected? So 1P means that there was a student that ranked Graham Parks first, had proximity priority, and was rejected. Okay? 1R means that there was a student that ranked Haggerty first and didn't have any type of priority, so this is regular, and was rejected. So here we can look the same thing for paid lunch and free lunch students, and we can see that there are a set of competitive schools that are very competitive for paid lunch kids that are not that competitive for free lunch kids. This means that for Graham Parks, in a typical year, if you rank it anywhere that is third, you may still get in because NR is nobody rejected. Okay, so now suppose that you have a kid and you really like Graham Parks, like most people, and you say, well, but I live close to Haggerty and I have proximity priority at Haggerty. Okay, so if I rank Haggerty, I will say, well, I'm going to have priority, so I'll probably beat the marginal guy, and I can get Haggerty with a very high chance. But if I run Graham-Perks first, well, it happens that the guy that they're rejecting already has proximity priority. So if I don't have proximity priority, maybe I'm not going to get there either. So this is saying that, okay, so you really need to think what you're going to do with your first rank, because you can have, with that rank, you can have a good shot at a very competitive school. But then if you think, what should I do with my second rank? Well, your second rank is pretty much useless among the competitive schools. And actually, whatever you do, it doesn't matter so much for the non-competitive schools. Even if you rank it second or third, you may still get in with very high chance. So this gives us a very nice way to think about strategic behavior just by looking at what people rank first. Okay, so here you see a discontinuity. Let me explain where the discontinuity is coming from. What we do is we look at every single pair of student school, and we look at the school, and we say, okay, is this school one of the two closest schools where this student has priority? If the answer is yes, we're going to compute the distance of the student to the school, compute the distance of that student to the third closest school, and take the difference and write it as a negative number, and say, okay, for this student and this school, this student was at a minus 0.5 miles from the proximity boundary. If there is a student that if we have a school that is the third or fourth or fifth closest school, what we're going to look at is at the school that is your second closest school, take the difference of the distance between the two, and write it as here as a 1, and say, okay, this school is 1 mile from the proximity boundary. And we're going to say, okay, we're going to write a dependent variable that is where you rank or not that school first. And what we see here, a simple linear probability model where we have bins, and here we have the means and the standard and the confidence interval for the coefficient. That basically, if you have a student that the second school and the third school are sort of at the same distance, this student is much more likely to rank the school where he has priority first than the third school. Okay. So now we say, okay, well, this is very interesting, but maybe this also happens for other ranks. Maybe if we do the same thing but construct a dependent variable that is where that school was ranked second, we also get something similar. And when we do it, we don't see any discontinuity. Similarly, if we just look at schools 2 and 3, we see a discontinuity. Over here, this is just considering the second closest school and the third closest school. And now we can say, okay, let's do a placebo test where we look at as if you were given priority only in the first school. So the school that you rank first. So let's look at the school that you are closest versus the school that is the second closest to you. And let's do the same exercise. And what we see is no discontinuity whatsoever. So here what we have is a school that is your first closest school that is 0.1 miles from the difference from the second closest school, and here you have the second closest school that is sort of the same distance. Well, because your priority doesn't change here and here, your behavior doesn't change much, which is what we would expect. So this evidence, I hope that allows us to at least question the benchmark of truthful behavior in this particular model, in this particular setting. So if you were to advise a parent in this market, or if you were talking to them and say, okay, what should I do in this mechanism? You should be trying to think about two things. First, think about the market, right? What is the probability that you would get into each school if you submit each possible report? Okay, that's just about the market. And then ask the parent about their preferences, whether it makes sense for them to take a long shot in a very competitive school, or it's better to just take a sure shot in a school that is less competitive. And let's see what they have. And this is going to suggest our estimation and identification strategy that is going to consist on 2 stages. First, estimate the probability of assignment as a function of the reported ranking, and then to estimate preferences based on the choices that people make under this uncertainty. So now we're going to do a little bit of theoretical work to show that we can do each of these 2 steps. So first step, we need to be able to assign, to estimate assignment probabilities. So let me give a theoretical foundation for what we're doing. We're going to be thinking of mechanisms that have the following components. Each student is going to submit a report. There is going to be this RI. Each student is going to have a priority type that is going to be this TI. And there's going to be some randomization that is going to be through a lottery that is going to be used to break ties. So the economy is a set of students, 1 to n, a set of schools, 0 to j, where 0 is the outside option, so you remain unassigned. And each school has capacity qj n, and we're going to assume that the outside option has unlimited capacity, so you can always remain unassigned if you want to. And mn minus 1 is what other people are doing. Okay? So it's the measure of the report and priority types of everyone else in the economy. Okay? So we can think of the probability of assignment as a vector valued function that tells you for this mechanism phi, if you have a report Ri and a priority type Ti, and your competitors, that is other students, are reporting according to n minus 1, this is the vector of probabilities that you would get. Okay? So now what we have to think is, okay, what is the typical data that we observe? When we think about estimating Bayesian games, we typically think that we observe many markets that are similar many times, so we can assume independence. But here, our data is going to look something different. We're going to have a few markets. There is 5 years of data, but a very large number of students. Very large, well, large. So now we need to think about as an approximation that works as n, that is the number of students, goes to infinity. And the problem that we face in this case is that the game changes with n, and therefore the strategies change with n, and that makes our problem a little bit more complicated. So what we're going to do instead, in order to try to avoid having the strategies to move around, is what we're going to say, look, as the economy gets large, agents are going to play an equilibrium of a game that we define to be the limit game. So that is what happens when the market is so large that you really don't have any influence on the market whatsoever. Okay? And what we're going to do is we're going to assume that agents play these equilibrium strategies of the limit game, and we're going to justify this based on two grounds. First, we're going to be able, so we're going to impose conditions on the mechanisms such that if the mechanism that we are analyzing satisfies this condition that I'm going to tell you in the next slide, then there are two things that happen. First, the equilibria of the limit game is also an epsilon equilibria of the finite game for a sufficiently large n. And the second one is that we can actually estimate this in a consistent way. Okay? And the condition that is going to bias that is this convergence condition. That is that basically, if we have a sequence of empirical measures mn minus 1 that converges in probability to the population measure m, then for each report and each priority type, we have that the vector of assignment probabilities of the finite economy evaluated at mn minus 1 converges in probability to the assignment probability of the limit game evaluated at the limit measure. Okay, so now this gives us two things right away. First, consistency. Now we have a way to say, look, if you know the mechanism, you just plug in what other people are doing, and you can estimate this, and you know that it's going to be consistent. And at the same time, we can show that if an equilibrium of the limit game induced by phi infinity is an epsilon equilibrium of this game, the finite game with n, sufficiently large. Okay, so we have for each n, there's an n star such that for n greater than n star, there's an epsilon equilibrium. So we're going to verify in the paper, we're going to go to some theoretical effort to verify that this condition is satisfied for a large class of mechanisms that include the Boston student proposing different acceptance, among other used mechanisms, including the one that we have. Okay? So, yes?
Is this convergence result the result of some deeper behavioral model, or is this just a technical condition?
There are two things. There are two things that are going on. One is that you as an individual are not able to affect the assignment probabilities of other. So it's like a large market assumption that your influence on what other people's probabilities is going to zero. And that there is some smoothing out of the assignment probabilities that is given by an actual randomization device of the mechanism. So we need those two things. But that's essentially the proof with a lot of math. But those two things are the two economic intuitions behind the proof that we have. Yeah, thanks. It was perfect question to avoid all this. So it was perfect. We agreed on that. With that, I said, okay, I can estimate assignment probabilities in a consistent way. So now let's think, once I have those, let's think if I can identify and estimate preferences. So let me again work a little bit. So we have a student observables in market B. There is just a vector Z that has, say, you could think of Ci1b as the distance of student I from its home to school 1, and then an observable vector that is Xi that is in the direction of IO as having like an observable product characteristic or something like that. So we have a random utility model, and what we want to identify is a joint distribution of the valuation of each student for each school. Okay, so this is a valuation. This is a vector V that contains one element for each school, with the outside option being normalized to 0, and we're interested about the joint distribution of those valuations. Okay, so those are a notion of preferences. So we have only one market, so really we can condition on an observable school and observable characteristics, and we're going to assume technical assumption that the joint distribution of valuations admits a density function. Okay, suppose that we have 3 schools: school 1, school 2, and school 0, that is the outside option. Okay, so now I told you that each report that you submit to the mechanism is associated with a lottery, with an assignment probability over different schools, so that you could represent each report by a point in this graph. Okay, in this plot. And this is what I've done there. I have many plots. There are many possible lotteries, many possible reports that you can submit to the mechanism. Okay? So now if I look at this and you remember your micro 101 class, well, you can think of two commodities as being units of probabilities of school 1 and units of probability of school 2. And if you like both, you would want to have a lottery that gives you a lot of probability of both. Okay? So now you're an expected utility maximizer. So that means that your indifference curves in this graph are linear functions. Okay, so if your indifference curves are linear functions, I can find an indifference curve that makes you indifferent between this lottery and that lottery. Okay, and another thing that we know from micro is that the vector that is orthogonal to your indifference curve is the vector of marginal utilities. Okay, so we're going to have a vector of marginal utilities that looks like this, and this is something that I'm going to represent in the space of utilities, B1 and B2, this vector is something that goes like this. Okay, so now I'm going to look at the different set of lotteries, these two, and I'm going to have something like this. So a consumer that has this indifference curve is going to be indifferent between this lottery and that lottery. So now, for some reason, it's negative, but that doesn't matter. That means that this individual doesn't like too much school 2. So now I can again do the vector of marginal utilities that is orthogonal to the indifference curve, and I'm going to end up with another vector looks like this. So essentially, if I observe in the data that you as a student are choosing this lottery, then that means that your vector of valuations, your vector V, is in this cone. In the cone spanned by these two vectors. Okay, so with that in mind, we can give a mathematical formulation, and we're going to say that your valuation has to be in the normal cone that is to this lottery respect to the convex hull and the rest of lotteries. But this is just this, that by looking at the indifference curves, we can just figure out where your vector valuation should be. So now, now we can say, okay, we have a normalization. What we can do, we can normalize the length of the vector to be 1. So this is by saying that, okay, if you give me a data set and you do the first step, you calculate each probability, then what you can do is look at each lottery that was chosen, look at how many people chose that lottery, and then figure out how many people is in this is in each of these arcs in the unit circle, right? That's all the information that your data gives you, okay? So now the question is, how can you use additional variation in the data to actually identify preferences, to actually identify the distribution of valuations? So what we're going to use here is a special regressor. So we're going to have a variable that is going to have that is going to enter additively in the utility function. So what does it mean? That you are going to be risk neutral with respect to this object. For instance, we can have we're going to use distance in our application as being the variable that you're risk neutral about. Okay. So and if you want to do welfare, if you really want to, you can think of this as being a distance metric utility, so that you can measure utility in terms of distance if you're forced to do that. So now we're going to think, okay, let me condition on Z2. I don't care about that. These are consumer characteristics that are fixed. I'm just going to care about the vector of distances Z1, okay? And I'm going to think that, okay, if I look at a lottery, there is this lottery. This lottery is associated with a cone. There is this cone over here that I represent with a letter C over here. And I'm going to be looking at individuals that are located at a particular vector of distances to each school. So this is something that I observe. I observe the number of people that chose lottery X, given that they had this vector of distances to each school. And this has to be, okay, the number of people that have valuations in that cone, okay? And I'm integrating over the density of V. Okay, so that's something that that my model tells me and my data tells me from the fact that I can see how many people chooses this report and given this vector of distances. So now I can make a simple change of variables and I can end up with nu as the density here, and I can end up with nu minus Z1 that belongs in the cone. So what this is saying is that now what I need to identify is the density of nu. This is the only random thing that I have. And that the vector of Z is going to be able to move around the cone, to move around the cone over which I'm integrating. Okay. So now what this is saying is that essentially I can write nu1, nu2, and look at C1, C2. And say, okay, I'm going to look at how many people chose this lottery, given that they had this vector of distances, and that number is going to be the probability accumulated under this cone, given the density G. Okay, so now what I can do is say, okay, suppose that I'm going to look at a different set of individuals. I'm going to look at a set of individuals that are located at this vector of distances that puts them right here. Okay, and I'm going to look at how many people that are located at this vector of distances chooses the same lottery, and I'm going to subtract that from this, and I'm going to end up with the same cone, but now located here. So what I'm going to end up is with the density, with the mass of people that are in this area. Okay. If you think about it, a displacement in this line means that I'm essentially moving. I'm keeping people in difference between these two lotteries. Then I'm going to do the same thing, but I'm going to be focusing on people that are located at this vector of distances, and I'm going to end up with a cone that looks like this. Okay, and I'm going to subtract that. So I'm going to end up with this minus this. But this is just another cone that is just the previous one, where I can just read off my data how many people chose this lottery, given that they were located at this Z and this Z2. Okay, so this is saying that I can get the mass of people in this area, and because I can make this value as small as possible, I can actually get the density of G anywhere where I see variation in Z. So this is the identification result. That it gets more complicated when, and it gets more complicated when you have higher dimensions. But what we can show is that it still applies for high dimensions, and I will be happy to talk about that afterwards. So now let me tell you a little bit about what we find in Cambridge. So let me tell you about what we do to estimation, and actually tell you about the estimates of the numbers that we get for Cambridge. So we have a first stage that, as I told you, is just looking at the mechanism over there, just plugging in what other people are doing. We think that it's a better approximation to just resample from the data other students, just because we think that it's a better approximation to the uncertainty that people may have. And we're going to compute for each report and each type your assignment probability to each school, okay? And we show that Cambridge mechanism satisfies condition 1, and this is what we get. So what we get, if you look at here, is that for Graham Parks, if you rank it second, there's no way you're going to get in. And even these schools, if you rank them second, you have very low probability of getting in. But if you're a paid lunch kid, there is a 0.7% chance that even if you ranked Graham Park second and you didn't get into your first choice, you may still get into to Graham Park. So this is the conditional probability of getting into Graham Park's condition if you ranked second, conditional on the fact that you were rejected by your first school. Okay, so this is saying, this is what I try to say with this is that the markets that paid lunch and non-paid lunch kids face is very different. Paid lunch kids face a much competitive market than free lunch kids. And here what we're going to do is we're going to estimate a demand function, and we're going to assume a simple linear specification where basically the value of student I for school J we're going to include interactions between school dummies and demographic characteristics. So this would be like kids whose parents speak Spanish at home interacted with each school. Then a distance that enters additively and a probit random term that is distributed normal with mean 0 and variance sigma. And we're going to specify some diffuse priors for beta and for sigma. And what we're going to be looking is at each individual in the data, we're going to look the lottery that he chose, find the associated cone to the lottery that he chose, and we're going to do what Bayesians call data augmentation, that is start with a guess VI within that cone, so that we know that initial guess doesn't violate what we see in the data. And then we're going to run the Gibbs sampler that is simply estimate the equation above by seemingly a related equation, construct the posterior, draw from the posterior, and then we're going to modify the first step of Rossi, McCulloch, and Allenby. That is basically what we're going to do is if we have that before your previous case, we had you here, there is V1 and V2. We're going to first draw V2 conditional on V1, so we're going to draw V1 and V2 from this set, and then we're going to, once we get a new draw, we're going to draw again from this set to keep you in the set, to keep you in the cone. So this is we're not innovating here. I'm just trying to tell you exactly what we did. So now we get some results. We get the estimates, and we ask ourselves, okay, now how many people are actually ranking the school that they prefer first, and how many times are they getting assigned to it? So if we look at Graham Parks, there are 20% of people that actually think that Graham Parks is the school that they prefer, but only 14% of people are actually ranking it first, and we even simulate that this number is 14.4, so a little bit higher. And if we look at the number of people that rank a school first and gets assigned to that school, so that's this number, 83% of the kids. But if we think about what is the number of people that actually prefer that school to start with, so that's their preferred school, that number is 74%. So there's a 9% of people that get assigned to their first choice, but that was not their preferred choice because they decided to rank something different. And if we look at the disaggregation between the paid lunch and free lunch, we're going to see that most of the action is coming from the paid lunch. Free lunch kids, the difference is very small. Paid lunch kids, the difference is bigger. So now the next question is, okay, suppose that we go ahead and simulate the counterfactual situation where we have deferred acceptance instead of the Boston mechanism or the Cambridge mechanism that we have. So what we do is we estimate and simulate the model, and there are two different behavioral assumptions. One is assuming that people behave truthfully, and then we construct the counterfactual under that assumption, meaning that people behave truthfully, and then we're going to estimate and simulate the counterfactual, assuming that people are sophisticated, so that people follow the reasoning that we suggested during the paper. So, and what I want to show you here is that two things. Is that if you really believe that people are naive, so that people are truthful, and you do the whole analysis, you're going to think, well, the Cambridge mechanism is kind of bad, because even if it's much better at assigning people to their first choice, it does a very bad job at assigning people to their second choice. Okay? And this is by the nature of the Cambridge mechanism. The Cambridge mechanism tries to assign as many people as their first choice as possible. But now, if you think that people are actually sophisticated, then you're going to have the following. You're going to have that this is first choice now. This is their actual first choice. That people are, that paid lunch kids at least, are the Cambridge mechanism that's better in assigning them to their first choice, but it doesn't do as bad at assigning them to the second choice. So the difference is 17% and 15%. And then the idea here is that if you're sophisticated, you have a second choice that is good enough, and that that you can get into because it's sort of a safe shot. You actually go ahead and rank it. And you don't let the mechanism to figure out that that's something good for you, but you just go ahead and rank it. And this is why the paid lunch, the Cambridge mechanism doesn't do such a bad job at assigning people as the second choice. So if you want to, remember that we had a distance metric utility. If you want to really think, okay, a measure of aggregate welfare, we get that paid lunch kids would be worse off if you change the mechanism for a deferred acceptance mechanism. And this is because many kids really like Graham Parks, and they say, you know what, no matter what, I'm going to rank Graham Parks first. And they get it with high probability because that provides the right incentives to people that like Graham Parks but not so much to actually go ahead and choose something else. Okay? So, and if you look at this, well, I mean, so there are going to be some winners, some losers. We're working to provide a bit more decomposition on who wins and who loses. But your median paid lunch kids would actually be harmed by a change to deferred acceptance. So let me conclude by saying that we can think of reporting a rank order list as a choice over lotteries, and this may be potentially generalizable to our settings, that we can identify and estimate preferences in a class of manipulable mechanisms, and that actually the Gibbs sampler becomes very handy to do this. And we understand that we are assuming sophistication, but we think there is a better alternative to approaches where we think that people are truthful, even if the mechanism provides them with strong incentives not to be truthful. And we, in an application to Cambridge public elementary schools, we find direct evidence of strategic incentives and strategic behavior. And we find that treating reports as truthful might actually overestimate the fraction of people that are assigned to the true top choice. Less people are assigned to a true top choice. Paid lunch kids face more competition and more complex strategic incentives. And relative to the algorithm in place, deferred acceptance would actually harm your median paid lunch kids. Thank you.
Thank you very much.
All right, great. This was a lot of fun to spend some time on this paper. I'm at a great advantage because I have Paulo about 10 feet away from my office for the year, which is great in many ways, but it's great to be able to talk to him about what's going on. And he and I have had several conversations about this project over the last several days. So let me just say a few things in general about this. So first of all, I think from a broad perspective, this is the way everybody in this room, I think, would say you ought to attack this kind of a problem. Think carefully about the model and the strategic incentives that are faced by the players, the families, and the game. And try to take account of that and try to learn something about preferences from their actual behavior in order to guide mechanism design. So this is an active area of research where there is a lot of input from economists, mostly theorists. One thing we do know from theory is that the details matter. And some people seem to have a little bit of a religion about which type of school choice mechanism is the one that ought to be used. There's some casual empiricism, mostly done by theorists, and That's the kind of thing that makes many of the people in this room cringe. And there's very little guidance from careful empirical work as to what's a good school choice mechanism, who is helped, who is hurt, what are the real trade-offs in practice, rather than just in theory. And this paper is a real tour de force. So it starts with the theory, there's the approximation result, dealing with the limit game as the approximation to the finite player game. There's a novel set of non-parametric identification results. There's a practical estimation approach with a pretty simple parametric model. And then there's some very careful empirical work that combines this descriptive RD type analysis with the full estimation of the model to get to some really interesting positive and normative questions. So just a little bit of background for those of you who haven't followed this school choice mechanism design literature, and this is not my area of expertise either, but I'm at least somewhat aware of what's going on there. So one of the things that comes out of this literature is that this is where a little bit of the religion comes into play. There's a belief that mechanisms that require families to strategize in order to get good outcomes are sometimes viewed as bad, and that may or may not be true. But the argument in any case is that families do this once, twice in their lifetimes. We may not expect them to do very well. That may cause them to do badly, and there's something inherently unfair in the fact that families that are able to strategize well could end up well off at potentially harming the families who are less well off, or less sophisticated. And so that's led to a belief that something that is strategy proof, meaning it's weakly dominant to report truthfully, that's preferred, and Gale Shapley deferred acceptance algorithm is the thing that's mostly promoted. On the other hand, deferred acceptance has some weaknesses. In particular, it allocates slots based only on ordinal preferences. And you can show that that can do very badly. So in a simple environment, for example, where everyone agrees, all the students agree on which schools are the best ones, and schools basically don't care, they're just admitting students, or they're just rationing the slots that they have available, then deferred acceptance is equivalent to completely random allocation. So that's ex post Pareto efficient, but so is anything. So that's not a very good criterion. So it's been shown that you can do much better in some cases using the Boxton mechanism or other things that actually allow students or families to express preferences over lotteries. Say that I'm willing to top rank my second most preferred school because actually I don't care that much about the difference between first and second. Okay, so the identification argument here is sort of a standard thing in some ways. There's some elements of the problem here that look like discrete choice. Students are choosing from a finite list of possible options, which are all of the possible lists that they could submit. So a ranking that they could submit, and of course a ranking that you submit then maps to a lottery. So I think this is a nice way of thinking about it, that it's a discrete choice among what is possibly a large but finite set of lotteries. So if you have 10 schools and 3 spots to rank, it's 10 times 9 times 8, it's 720 different choices, discrete choices to select from. But there's also some extra structure, which is that the preference over the lotteries are not arbitrary in the way that we would think about in the case of discrete choice, but they're built up from preferences over a smaller set of schools, maybe 10 schools. And then the admissions probabilities that are going to arise in equilibrium. So these admission probabilities, part of the trick here is to recognize that when we see data from these school choice mechanisms, those admissions probabilities are observables. And so we're going to use that. We're going to have agents who are optimizing against those observable probabilities. And in that case, it looks a little bit more like auctions. Okay? And the identification argument uses some ideas from both the random utility discrete choice setting and also some ideas from auctions. And you got a flavor of it in the presentation. There's some really beautiful arguments, theoretical arguments that go on there. Okay, so I have 3 comments. The first concerns this use of the limit game as an approximation. And as I said, the authors are approximating the finite player game with the limit game where there's a continuum of players. And there are certainly applications where this would be a terrible idea. So most auction applications or oligopoly applications, this would be assuming away all of the interesting stuff. Here, I don't think it is. On the other hand, I'm a little bit unsure. And let me just suggest an alternative and tell you why I'm unsure. So a possible alternative is to assume that the players are playing the finite player game, even if it's a large number of players. but to imagine that the players recognize that actually they're playing against a large number of opponents, and those opponents are drawing their valuations for different schools from some common knowledge population distribution. That is not so different from what the authors are doing, but it is different, and it's much more like what Ali Hortatsu has done with various co-authors in the case of auctions. I'd like to see what happens here, and I would be very comforted if we were shown that nothing went wrong. If nothing goes wrong, then it seems like we should just do that, because it's sort of, we know there's nothing wrong with that. On the other hand, if something does go wrong, then I'm a little worried, because then I'm not sure, we're in this situation where we're saying, well, we kind of need this approximation, but still it doesn't matter that we're making the approximation, and that's kind of a narrow window to fit into where we both need it, because it's buying us something, but it doesn't matter because it's not buying us too much. The second thing I'll just mention, I think this is obvious, it's assumed here that location is exogenous, and we think location isn't exogenous. I mean, there are lots of literatures that think about residential location decisions which depend specifically on what schools are available. And I think it's plausible that locations within one of these priority zones is exogenous, or at least exogenous enough. That's what we usually mean by exogenous. Once you're in the priority zone, maybe it does. Your preferences aren't really very correlated with whether you're half a mile away or a quarter mile away. And I'd be interested in seeing whether we could do some analysis, at least as a robustness analysis, that uses only that variation rather than the variation across these boundaries. So this is really throwing out all the variation that we use in the RD analysis and only focusing on the rest of the variation. Okay, so the last comment, which is maybe slightly more helpful, I don't know if it's more helpful, but it's maybe something more worth thinking about, is back to this idea of whether we want to think about this as in a discrete choice way or in a more auction way. And this has to do with preference shocks. In a discrete choice model, these preference shocks, we call them preference shocks, but actually since the beginning of time, it's always been valid to, one of the motivations, in fact, was that these could represent some sort of optimization error. That people don't always choose what would be objectively best for them, but they tend to produce they tend to choose what's best for them, and with some probability they choose something which isn't best. It's unlikely they choose something that's truly horrible for them. These preference shocks provide a formal way to rationalize that kind of idea. That might be attractive here for two reasons. One, it softens an assumption that we might worry about in this context, which is that families are optimizing perfectly. Again, there are cases where we think perfect optimization is reasonable because we're talking about the behavior of firms who are selected into this activity and who have a lot of practice. That's not the situation that we have here. The other thing is that, strictly speaking, there are observations in the data that reject the current model. There are families who make choices which they should not make because they could choose something which would just be strictly better. The current modeling approach is more like what's done in auctions, where there's no randomness at the point of optimization. It's all random shocks to preferences, and then there's perfect optimization afterwards. And I wonder whether there's a way to proceed which is more like the discrete choice environment, where we're really thinking of this as being a discrete choice among a long but finite set of options, which are all the possible lotteries. Okay, so I'm indexing here all of these lotteries by L, and I have here a utility, a conditional utility of household I for lottery L, where we're summing over all of the schools. These are the probabilities that student I, based on her priority status, gets into school J, conditional on ranking, choosing option lottery L. This is the valuation that this student has for school J. That's exactly the object that was in the model before, same notation. Plus now an epsilon, which is different from their epsilon. This is the usual shock that we put into discrete choice models. Okay, this seems like, it looks like pretty much like a standard random utility discrete choice model where we have some random coefficients V, which are hitting some student and choice specific characteristics, which are these choice specific probabilities of admission. It's better than that in some ways in that we actually have a model which we're using to generate these random coefficients. We don't have to say they come from some arbitrary joint distribution. We're building up those preferences from preferences over a smaller set of schools, and I think that actually is going to help. And I wonder whether it's possible to go this way in order to relax this assumption of perfect optimization. Okay, so to wrap up, I think this is a great project. It combines some really creative theoretical work with some serious and empirical work on questions that I think a lot of economists and policymakers care about. This is an 80-page paper. It needs to be 120 pages, which is another way of saying I think probably it should be 2 papers. And I really think there's enough for 2 big papers here. And I look forward to seeing the next version of those 2 papers.